In the previous lecture, we have discussed in very detail in some of the videos the concept of antiferromagnetism. And now today we are going to start the idea of ferrimagnetism. Actually, when you talk about ferrimagnetism, you will see that actually this ferrimagnetism is a special case of antiferromagnetism. What happens, how the spins are arranged in case of antiferromagnetism, you have already discussed. And what is the difference between the arrangement of a spin in ferrimagnetic material and antiferromagnetic material, you will learn now. Actually, we have seen that in case of antiferromagnetic material, the spins are equal and opposite. The neighboring spins are equal and opposite. And so, the net magnetization of a given specimen of an antiferromagnetic material is zero. But when you talk about the ferrimagnetism, there will be a slight difference, as you can see in this figure, that here you can see this first spin is up and its neighboring spin is down. And again you can see this neighboring spin is also down. Then again this spin is up and this is the down spin. But as the length of the spin vector has been shown different, what actually it refers? Actually in this case we assume that the magnitude of the two neighboring spins are not equal, although they were equal in case of antiferromagnetism. But in case of ferrimagnetic material, the magnitude of the spins are unequal. Okay? And so, when the magnitude of the spins will be unequal, you know, when we will find the total spin, they will not cancel one another, but there will be a resultant magnetization or magnetic moment. Okay? So I have mentioned it here that you can see ferromagnetism is a special case of antiferromagnetism. Ferrimagnetism is a special case of antiferromagnetism. It occurs when the magnetization of the two sublattices in terms of which we consider the antiferromagnetic crystals are unequal. Mark it, these are unequal in magnitude, and consequently the net magnetization of the crystal has a non-zero value. Okay? The net magnetization has a non-zero value. Okay? So you can say that the ferrimagnetic crystals are thus the magnetic compounds consisting of two or more different kind of atoms, okay, and having a permanent dipole moment. Okay, actually the difference in magnitude can arise in several ways, but in this figure I have shown only one illustration, but there may be several arrangement of spins so that the resultant magnetization will be non-zero. Okay. So, in fact, if the magnetization of different sublattices do not cancel each other in an antiferromagnetic spin array, there appeared a kind of ferromagnetism as a result of antiferromagnetic coupling, and this is termed as ferrimagnetism. Okay? Actually, the well-known scientist Neel pointed out that ferromagnetism of ferrites is due to this mechanism. Okay? So, what is this ferrimagnetism? I hope you have understand. But now we will see the particular example of this ferromagnetic material. Actually, the well-known, the most common example of this ferrimagnetic material are ferrites. Okay? So in this lecture we will see only the structure of ferrites, and after that we will discuss the saturation, magnetization of not saturation but spontaneous magnetization of ferrites. Okay, and after that, in the second lecture, we will see the proper theory, or you can say the explanation of ferrimagnetism. Sorry, I am suffering from cold, so don't mind. Okay, so I was telling you that in this lecture we will see only the idea of the structure of ferrites, which is actually a common example of ferrimagnetic material, and after that we will see also the concept of saturation magnetization in this ferrimagnetic material. But the second lecture on this ferrimagnetism will be the most important, and that will be actually the explanation of this ferrimagnetism on the basis of molecular field theory, where we will calculate the ferrimagnetic susceptibility and the Curie temperature. Okay, so now let us see. First of all, the ferrimagnetic materials, which is commonly called ferrites. Okay, actually ferrites and garnets are two groups of materials which are the common example of ferrimagnetic material. Okay, so which type of material will be a ferrimagnetic material or a ferrimagnetic crystal? Let us see. Actually, the ferrimagnetic crystals are magnetic compounds consisting of two or more different kinds of atoms. Okay, and chemically they are expressed as this: Me double plus Fe2 triple plus O4. This is the general chemical formula for the ferrites. Okay, actually in this formula, what is this Me double plus? Actually, Me double plus is a suitable divalent metal ion. For example, Me double plus may be Co double plus, it may be Mn double plus, it may be Ni double plus, Fe double plus, Zn double plus, Cd double plus, Mg double plus. Okay, so Me double plus actually represents in general any divalent metal ion. For example, I have mentioned here some of those. Okay, and this Fe2 triple plus, this is actually the trivalent ferric ion. Okay, so you can think that in a ferrite, Fe2 triple plus O4 will be always present. Okay, but at the place of Me double plus there may be a suitable divalent metal ion, of which I have given here some of the examples. Okay, for example, if you insert Ni double plus at the place of Me double plus, then the resulting compound is called nickel ferrite. Okay, and similarly, if you will replace this Me double plus by this Fe double plus, which is actually the ferrous ion. Okay, Fe2 triple plus is the ferric ion and Fe double plus is the ferrous ion. Okay, when this Me double plus will be replaced by Fe double plus, then this special case of compound is called ferrous ferrite. Okay, and it is written like this: this is Fe double plus Fe2 triple plus O4, or in more familiar symbol it is written as Fe3O4. Okay, chemically this is written as Fe3O4. But when you will write Fe double plus Fe2 triple plus O4, then actually it represents its structure. That in this ferrous ferrite there are one ion of ferrous ion Fe double plus, okay, and one ferric ion and this O4. Okay. So these are some of the examples of ferrimagnetic material. Now we will see the structure of ferrites. Okay. Actually, you know that for the determination of structure of any crystal, X-ray crystallography is the most suitable means, or it is the most important experimental technique to determine the structure of a crystal. So actually the structure of ferrites have been also obtained or found by X-ray crystallography. Actually, when X-ray crystallography, we study the structure of ferrite via this X-ray crystallography, then it is found that ferrites have usually the structure which may be described as a face-centered cubic structure, FCC structure, of oxygen ions packed closely together with much smaller divalent and trivalent metal ions in the interstitial site, as you can see here. Here actually I have shown that this hollow sphere or this circle represents the oxygen ion O double minus, and this shaded sphere represents the Mg double plus ion, and this solid sphere represents the Al triple ion. Okay, so this is the crystal structure of the mineral. Actually, MgAl2O4. MgAl2O4. In this figure, I have shown the crystal structure of MgAl2O4. Okay, you can see that Mg double plus ion occupy the tetrahedral sites. Mg double plus, these are the Mg plus ions, and these occupy the tetrahedral sites. Okay, and each of Mg double plus ion is surrounded by 4 oxygen ions. Okay, 4 oxygen ions. You can see that when you see this is your Mg double plus, and then this is oxygen ion, this is oxygen ion, this is oxygen ion, this is oxygen ion. So in this way, each Mg double plus ion is surrounded by 4 oxygen ions. Okay, and this Al triple plus ions occupy octahedral sites. Okay, octahedral sites. You can see these are these small spheres represent the Al triples ions, and these are actually at the position of octahedral sites. Okay, and each of these is surrounded by 6 oxygen ions. Okay, actually we will see later on that this is a normal spinel structure. We will see later on. In fact, when you talk about the structure of ferrites, then this structure is called a spinel structure. Okay, after the name of this mineral MgAl2O4. Okay, in which this spinel structure was first of all discovered. Actually, this spinel structure is of 2 types. Okay, first one is called regular spinel structure or the normal spinel structure, and the second one is called inverse spinel structure. Okay, inverse spinel structure. Actually, in a regular spinel structure, you can see the interstitial site is surrounded by 4 oxygen ions. Okay, and in the inverse spinel structure, there are 6 oxygen ions disposed at the 6 vertices of an octahedron. Okay, this is the basic difference between the normal spinel structure and the inverse spinel structure. Also, if we denote these interstitial sites say by A and B, okay, it means if you say that the normal spinel interstitial site is denoted by A and the inverse is denoted by B, okay, then actually there are 64A and 32B sites in the unit cell of this structure. Remember this, okay? Actually, the unit cell is composed of 32 oxygen ions, okay? But out of these 32 oxygen ions, only 24 interstitial sites are occupied. And among these 24 interstitial sites, 16 are at B sites and 8 are A sites, at A sites. Okay? Now, a reference to the chemical formula suggests that in the unit cell composed of 32 oxygen ions, there are 16 Fe triple plus ions and 8 Me double plus ions. Okay? Actually, the distribution of these 24 cations among 24 interstitial sites would be one of the following simple cases. See, if you talk about the regular structure, then at A sites there will be 8 Me double plus ion, okay, and at B site there will be 16 Fe triple plus, okay. For example, you can take at the place of this Me double plus, you can take Cd or Zn, okay, or you can also take this Ni, okay, you can take Mg at the place of this Me, okay. So when we will take Cd, that will be called cadmium ferrite. If you will take Zn at the place of Me, then it will be called zinc ferrite. Okay? And so its symbol is like Me double plus Fe2 triple plus O4. Okay? And in case of inverse structure, at A sites, there are 8 Fe triple plus. Okay? And at B sites, there will be 8 Me double plus, 8 Fe triple plus. Okay, and this is actually called the ferrous ferrite, and its chemical symbol is Fe triple plus, Fe triple plus, Me double plus, okay, O4. Okay, so these are basically the two types of spinel structure. But in practice, more usually we find the intermediate arrangements. When you say intermediate arrangement, that will be just a mixture of these two types of structure. Okay? An intermediate case of these two arrangements is taken of this type. This is the general formula or general symbol for the intermediate arrangement of the ferrites. This is Fex triple plus, Me1 minus X double plus, Fe2 minus X triple plus, Mex double plus O4. Okay. So these are some of the important facts regarding the structure of ferrites. Okay. Now we will talk about the saturation magnetization of these ferrites. Okay, or the ferrimagnetic material. When you talk about this saturation magnetization, you will think that actually these ferrites are essentially ionic compounds. Okay? And if the crystal is ionic, therefore the saturation magnetization will be decided, will be calculated by the number of unpaired spins of the ions. So if you want to find the saturation magnetization, first of all you have to see what is the total number of unpaired spins present in the ions. Okay? And that number of unpaired spins will decide the saturation magnetization. And to clarify this idea, let us take an example of magnetite, whose formula is Fe double plus Fe triple plus O4. Okay? It means this in this magnetite there are Fe double plus ions, okay, and Fe triple plus ions. Now see, this Fe double plus ion, you will see that there will be in this ion there will be 6 3d electrons, and in Fe triple ions there will be 5 3d electrons. Let us now explain it. How you can say that Fe double plus ion has 6 3d electrons? You know, Fe has atomic number 26. So when Fe is in its normal state, that is neutral Fe atom, then its electronic configuration is like this. This is 1s2, 2s2, 2p6, 3s2, 4s2, and 3d6. Okay? Actually, I have written this 4s2 before 3d6 because you know the energy level or energy of 3d subcell is greater than that of 4s, and therefore 4s2 has been written earlier. Okay? Sorry. Now, this is actually the configuration of this neutral Fe atom. Just I am taking a glass of water. Sorry. Now, see the electronic configuration of this ferrous ion, Fe double plus. When you say Fe double plus ion, it means you have removed the 2 electrons. And think, which 2 electrons will be removed? Actually, as this 4s2 electron is more loosely bonded to the nucleus. Okay? And this is the valence electron. So first of all, this electron, 2 electrons present in 4s subcell will be removed. So the electronic configuration of Fe double plus ion is like this. You can see this is 1s2, 2s2, 2p6, 3s2, 3d6. Okay? So in the 3d subcell of Fe double plus ion there are 6 electrons, which I have mentioned it here. Okay? Now, when you talk about ferric ion, Fe triple plus. Fe triple plus means you have removed the 3 electrons from this Fe. So there will be only 23 electrons, and that extra 1 electron will be removed from this 3d subcell. So now in 3d subcell there will be only 5 electrons. Okay? So I have written here that this Fe triple plus ion contains 5 3d electrons. Okay? Now you know, you have definitely studied in your course on chemistry that in any d subcell, the maximum number of electron can be 10. D subcell can contain maximum number of electron which is equal to 10. You can understand how you can say that the maximum number of electron contained in this D subcell will be 10. You can understand. You know, for this D cell or subcell, the orbital angular momentum quantum number L is equal to 2. You know it? Okay. And if L is 2, then the orbital magnetic quantum number, which is denoted by the symbol ml. You know, for a given value of L, there are 2L plus 1 values of ml. And those 2L plus 1 values are from minus L to plus L at a step of 1. Okay, at a step of 1. So, what is the total number of ml for L equal to 2? That will be 2L plus 1. So, this is 2 times 2 plus 1, which is equal to 5. So, ml has 5 values. ml has 5 values. Okay. And therefore, you can divide this D subcell in 5 boxes. 1, 2, 3, 4 and 5. Okay. But for each value of ml, there will be 2 electrons for the 2 spin states, because you know ms is equal to plus minus 2, plus minus half. So I have mentioned it here that each of these can accommodate 2 electrons for ms equal to plus half and ms equal to minus half. That's why you can say that this since ml is equal to 5 and for each value of ml there will be 2 electrons for 2 opposite spins. Therefore, the total number of electrons which the 3D subcell can contain is equal to 10. Okay? So this is the maximum number 10. Okay? Now let us see. When you talk about this ferrous ion, Fe double plus, you have seen that this ferrous ion has 6 3D electrons. Now, how these 3D electrons will be actually distributed in this subcell? You can see that according to the Pauli's exclusion principle, first of all, each subcell each box will be filled with 1 electron with up spin, and the extra 6th electron will then paired with the first electron in the first box with down spin. Okay, so can you say that how many unpaired electrons are present in this case? There are 4 electrons. You can count 1, 2, 3 and 4. So you can see that in Fe double plus there are 4 unpaired electrons. Okay, 5 electrons with up spin, okay, and 6 with down spin. Okay. So in case of Fe double plus ion, there are 4 unpaired electrons or unpaired spin, you can say. Now see the configuration of this 3d5, which is in case of Fe triple plus ion. So if there are 5 electrons in 3d subcell, then all electrons will be with up spin, all are unpaired. So in this case of Fe triple plus ion, there are 5 unpaired electrons. Okay, but as there are 2 Fe triple plus, you know this is your formula. This is in fact when you talk about the ferrous, this is Fe2 triple plus and Fe double plus. So actually in this ferrite there are 2 Fe triple plus ions. Okay, and each Fe triple plus ion, you can see, contains 5 unpaired spin. So the 2 electrons will contain total 2 into 5, that is 10 unpaired spins. Okay. So the total number of unpaired electrons, or you can also say spin, unpaired electrons or spin, this will be equal to 10. Okay. So in case of this magnetite, there are 4 unpaired spin of this Fe double plus ion, okay, 4. And there are 10 unpaired spin of this Fe triple plus ion. So what is the total number of unpaired electrons or spins? Electrons or spins. This will be 10 plus 4, that is 14. Okay. Now, if you assume that each spin contribute 1 unit of magnetic moment in unit of Bohr magneton, then what will be the expected value of magnetic moment? Since there are 14 unpaired spins, so the expected saturation magnetic moment per molecule of Fe3O4 should be 14 mu b, where mu b, you know, this is Bohr magneton. This is the expected value. We guess it on the basis of the number of unpaired spin. But what is the experimental fact? What is the experimental result? Actually, experimental result does not agree with this value of expected saturation magnetic moment 14 mu b. Actually, experimental result shows that the magnetic moment of a molecule of Fe3O4 is equal to 4.08 mu b, not 14 mu b, 4.08. So this is almost equal to 4 mu b. You can see 4 mu b. And you can see this molecule of Fe3O4 has one ion of Fe double plus, okay, which contains 4 unpaired spin or unpaired electron. So it appears that this experimental value of magnetic moment is only due to the spin of Fe double plus ions, the unpaired spin of Fe double plus ion. It means there is no contribution of the spin of Fe triple plus ion in the saturation magnetic moment of this Fe3O4. Okay. So how you can say that only the unpaired spin of Fe double plus contribute to the magnetic moment of this magnetite, not the unpaired spin of Fe triple plus. Actually, this can be seen by this structure. You can see, actually this Fe triple plus ions has anti-parallel, ions are anti-parallel to each other, resulting in their mutual cancellation. Okay, mutual cancellation. You can see, I have shown here that 8 Fe triple plus ions spin, which is spin up, and these are actually at the tetrahedral interstitial. And there are also this 8 Fe triple plus ion with spin dome at octahedral interstitial. And so these two will, when this will be added, this will be 0 and no magnetic moment will be created. But the 8 Fe triple plus ions and their spin are, you can see, of a smaller magnitude than those of the Fe triple plus, and they are only in downward direction, as you can see. So only the unpaired spin of Fe double plus contribute to the magnetic moment of this magnetite. Okay. And so in this way we can explain the saturation magnetization of a ferrite. Okay. So this is all about what is this ferrimagnetism, how it arises, what is the structure or crystal structure of ferrites, okay, and how we can explain the saturation magnetization. Okay. This was actually an introductory part of the lecture on ferrimagnetism. But in the second part of the lecture, as I have told you, we will explain this ferrimagnetism by the molecular field theory, which will be just like the explanation of antiferromagnetism, and we will learn about the magnetic susceptibility of ferrimagnetic material and also about Curie temperature. Okay, thank you very much.